Welcome to the course of material selection for mechanical design. We are at the week 2 mechanical properties level, and here we have discussed about most of the important properties, but particularly we are concentrating now on properties which is related to vibration and damping, because as I have earlier also indicated you that many mechanical systems will be invariably subjected to dynamic loading, and vibration is ubiquitous in such a system. So, while choosing a material, we have to be aware of what type of a vibration it is subjected to and how do we choose materials related to it. In the last lecture, I have mainly focused on structural damping, and also I have defined the loss factor with in respect to that. Now, the structural damping is something which is so the structural damping is something which we generally use for metallic systems. Okay, so if I use metallic systems for my structure, then this becomes important. On the other hand, there are other type of applications where polymers are used, polymers or plastics. Okay, so such a case, more than structural damping, what is important there is called the viscoelastic material. Okay, so a material which works both as a solid as well as a fluid. Okay, so a metal, for example, okay, if it is working under ambient condition, then a metal behaves almost like a spring. Okay, so this is like a elastic material behavior, right? And you also know that how does the fluid works, a viscous fluid. For that we have seen that the damper model, right, the viscous damper model. So, that is a viscous fluid damping. Now, interestingly, a polymer in the ambient condition itself behaves like partly elastic and partly damping, and depending on different types of modeling, some of them we will see today, it will behave like this, or it can behave like this, or maybe many other complicated combinations of them. But essentially then this becomes something which is a marriage between viscosity and elasticity. So, it becomes viscoelastic. So, from the vibration point of view, if it is a metallic system, then you look for the structural damping. If it is a polymeric system, you look for the viscoelastic damping. Now, we have all along talked about that modulus of elasticity is something which is not going to get changed with time, but for a viscoelastic material, it has a time varying modulus of elasticity. So, we are going to see that the modulus of elasticity will be complex in nature, and how these changes happen, that can be actually obtained from the relaxation response of a viscoelastic material. So, we will also see some of the applications of such materials. So, let us look into what are these important viscoelastic materials. Well, the viscoelastic material which has a very high loss factor, highest is polyvinyl acetate PVA, then you have thiocol, you have butyl rubber 3M, you have butyl gums, polyisobutylene, DuPont, Viton A, silicon, neoprene, PU, silicone rubber, natural rubber. So, these are the materials which are generally used. Where are we going to use them? There are many varied applications, but I can tell you about one very critical application is in terms of sealing. Okay? So, these materials are used as a sealant, okay, between the two joining system. Okay? And then let us say you use it in a rocket, okay, or something which is subjected to a high thermal condition, and then also the dynamic condition, the vibrations are there. So, both temperature and vibration is going to work on it, and if this loss factor is very high, then it is going to be very useful as a sealing material. So, this is something where we very careful about its application. Now, similar to the creep of metal, now we are talking about creep of a polymer. Okay. So, what are the important things? That first of all, the creep diagram we see that it is not like a primary and secondary, but it is continuously traveling all along. Okay. And as the stress is increasing, it is becoming more and more prominent with respect to stress, and you can actually draw it very nicely like this. If you say this is the primary part, then even in the secondary part it is not stable, you see, and then the tertiary part till the rupture. So, you can actually now define a something which is called the creep compliance, okay, which is epsilon strain varying with time over the stress that you have kept in the system constant. So, epsilon t over sigma 0. So, a new sort of a property you can define through this, that is called the creep compliance. So, that is a creep compliance. Okay. Another important thing in creep compliance is the tau or the relaxation time, that actually tells how fast is this S curve. Some S curves can be very slow and some S curves can be very rapid. Okay. So, is this relaxation time, tau also plays a very important role in the creeping process. So, creep compliance and the relaxation time, the two things we have to consider in terms of a polymer. Now, how do we model such a system? Well, we can model the strain as having two parts. One part is constant sigma 0 over E, and another part is the viscous part, that is sigma 0 over eta times T. Okay. So, in this case, as I told you, that epsilon can be written as sigma 0 times 1 over E plus 1 T over eta, and hence epsilon over sigma 0, that will be the creep compliance Ct, and that will be 1 over E plus T over eta. So, that means you have an instantaneous term in the creep compliance which you are going to see immediately, and then you have another part which is going to increase with respect to time, and that depends so heavily on the loss factor, because the more the loss factor, the less will be the creep compliance. Okay. So, the loss factor plays a very important role in the creep part. Now, the stress strain relationship of a Kelvin-Voigt model of creep. So, that is something where the creep can be considered with respect to a spring and a damper in parallel. Okay. So, that is the Kelvin-Voigt model, and here the stress is proportional to the strain plus the strain rate. Okay. There are two parts in it, and assume that the K is E, then you are going to see that the sigma is actually E epsilon. Okay. So, K is E if you keep it. So, sigma is E epsilon plus eta epsilon dot. Okay. In fact, you can now solve this, you can find out epsilon t, which is sigma 0 over E 1 minus e to the power minus t over tau, and the retardation time tau here is eta over E. So, this actually shows what is the delayed intensity in the system. So, the more the value of the loss factor, the more will be the retardation time. Okay. And in other words, the smaller the modulus of elasticity will be, then also the retardation time will be longer in the system. Now, is this the only model? No, I told you that the realm of polymer is so complicated that you must know that there are many more models that are there. So, this is a, for example, a standard linear solid or a Zener model. These are all, you can see 1, 2, 3 parameters. So, these are all 3 parameter models. You can also have 4 parameter models, right. This is a 3 parameter model. So, where you have, again you have 2 stiffness and 1 damping, and you can have stiffness and damper in series, and you can have 1 stiffener, 2 damper, and that also in parallel and in series. So, these are the 4 variants of a Zener model that you can have for creep. The more these variations, I cannot directly write K as the modulus of elasticity. From experiments then, we have to figure out all these parametric values. So, this is the standard linear solid model of creep. So, that is the most popular model, SLS model, and what are the parameters we will need there? One is of course the E1, okay, and then the E2 you will need, and then you need the tau. Okay. So, these 3 parameter model is important, where you have instantaneous strain plus the delayed creep that is present in the system. Now, we also can look into the whole thing in the form of strain relaxation. Okay. So, what is creep? You are keeping the stress to be constant, right. And another way you can do is that you can actually allow the stress to relax. Okay. So, you keep the strain constant, and you see how the polymer is relaxing itself. So, this is also a counterpart of creep, actually, the stress relaxation. So, this is the converse of creep. Okay. And here the stress curves correspond to 3 different levels of constant strain now. Okay. So, it is somewhat, you see there you had this type of a curve, and here it is a reverse S curve that you can see here. And here, instead of the compliance, E relaxation becomes important, which is sigma t over epsilon 0. How stress is varying when you are keeping the strain to be constant. Okay. So, that we can again draw this, and we can also figure out how stress relaxation is taking place. Now, creep and stress relaxation tests are very convenient for studying the material response at long times, okay, but they are less accurate at shorter times. Dynamic test in which stress is resulting from a sinusoidal strain, okay, then this is in a short time response. So, viscoelastic polymer long time response is important, as well as the short time response is important. For a short time response, we actually we will go for a particular parameter which is called an angle delta, okay, and this delta is related to the loss factor of the material. So, this is something that we would look into it when the response is relatively faster in nature. Okay, if we look into the dynamic response of a polymer, so how we can do it? See, we can keep the strain varying now, okay, in a harmonic way. So, if we try to plot this, okay, that the polymer is now subjected to a strain which is varying continuously with time, epsilon, with some value, say epsilon 0, and then it is in a cosine mode, it is varying. Okay. So, I am varying the strain in a system, and then I am measuring what is going to be the stress with respect to time. Now, if you are a system which is metallic, where you are varying the strain, okay, and you are measuring the stress, it will be exactly at the same phase as the strain. Whereas, if this material is a polymeric material, you are going to see that it is going to have a sort of a phase difference in it. Okay, say for example, this is the point where you are supposed to get the 0 strain, you are going to see that it is going to have a slight phase difference in the system. The frequency does not change, but these amplitude position got shifted now from here to here. okay, and this shifting is by an amplitude of delta. So that the stress is now cos omega t plus delta, that is the phase, okay, and then tangent of that phase tan delta is actually related to sigma 0 double prime over sigma 0 prime, where sigma 0 prime is sigma 0 cos delta and sigma 0 double prime is sigma 0 sin delta. So, essentially you take the ratio, you get actually sigma 0 tan delta. So, that is how you can define the tan delta. So, now we see that we are going to have two different type of modulus now. One modulus is the real modulus, that is sigma 0 prime over epsilon 0, and another is the loss modulus, that is sigma 0 double prime over epsilon 0. So, you see, in comparison to a metal, the polymer is something which has two elastic moduli. One is the real or a storage modulus, another is a loss modulus. In other words, if you say everything from the polymeric point of view, then a metal will have very small loss modulus, but only predominantly it will have the real or the storage modulus. Whereas for a polymeric point of view, these two become significant. And then the significance of tan delta comes into picture. That is, the more the delta, the more is the significance of the tan delta value. Okay. Now, what is the maximum delta that is possible? I did not talk about that. You please think of it. Okay. So, if this becomes from a solid to fluid, then delta's maximum value, delta then becomes pi by 2. So, for anything which is at least some part is solid, then the delta will be less than pi by 2. That means for a fluidic system, there is completely 90-degree difference between stress and the strain. Okay. So, for and then delta equals to pi by 2, tan delta becomes infinite. So, as the delta increases, tan delta increases enormously. I told you earlier that the definition of loss factor, for it you have to calculate what is the work done per loading cycle, and that is the cyclic integral of sigma d epsilon, and then you can put actually d epsilon as d epsilon dt, and then you can write down these expressions of sigma in terms of the storage modulus, sigma in terms of the loss modulus, and also you know that what is the energy that is dissipated, which is because of the loss modulus pi sigma 0 double prime epsilon 0. So, you can get the W that is dissipated. So, W that is dissipated and work that is done, both of them you should be able to find out. You should be able to find out what is the maximum energy stored in the in-phase components. From this you will be able to see that will come out to be half sigma 0 epsilon 0 cos delta. So, now you know that the maximum energy that is stored in phase, you know that is what is the energy that is dissipated. Okay. These are the two parts that is actually there inside this expression, and then this ratio is definitely going to give you the loss factor. Okay. So, that is the way the loss factor will come into picture. There is another way also we can look into the loss factor, that the definition of stress is proportional to strain is no longer valid for a polymeric material. So, it is a generic definition of stress rates and strain rates, okay, and in it if you keep sigma as sigma 0 e raised to the power j omega t and strain as epsilon 0 e raised to the power j omega t, you will see that sigma 0 over epsilon 0 has both in the numerator as well as in the denominator frequency dependent terms, and hence you can actually simplify it in order to get a real part and a loss part. So, from the representation of these complex modulus of elasticity, what we can infer is that the stress strain relationship for polymeric material is actually not the Hooke's law relationship that we know, that sigma as E epsilon, but here there is there are rates of stresses and rates of strains also involved in the constitutive relationship of the system. So, E star is E prime plus J E double prime, okay, and eta, that is the loss factor, is tan delta, and that is E double prime over E prime, okay. So, that is the ratio between the loss modulus and the real modulus, okay. In fact, you can write the whole thing also in terms of the real modulus as E prime into 1 plus J eta, and similarly G star and B star will happen, but the relationship between E and B and J, G. So, you see, for this B star we have also written it as a bulk modulus K earlier, okay, and you see now we are using the stars each and every case, signifying that now for the polymers all these modulus are actually complex in nature, okay. So, that star is showing it, but the relationship between E star, B star and G star is same that I had earlier talked about for a real modulus system. So, thus we can actually keep these in mind, that whatever we have learned earlier for the stiffness part, it has a counterpart for polymer, and everything becomes complex, and that complex part is defined with the help of the loss factor or the tan delta. That is what is important for us. So, loss factor or tan delta thus plays a very important role. As I told you that the value of delta ranges between 0 to 90 degree, delta approaches 0 for purely elastic behavior, delta approaches 90 for purely viscous behavior. And if I try to see how this loss factor changes with respect to temperature, you would see that at a particular temperature this will have a peak value, okay. So, that temperature is also known as the glass transition temperature or TG. So, for a polymer this is important, you see, because below that or above that the loss factor is quite low. So, if I have to improve the loss factor of a polymer, I must know at what temperature it is going to be so effective, okay. Now, suppose the temperature is ambient and I want to introduce this and try to get a large loss factor, then I can also play with the frequency of the system. So, there is a frequency temperature superimposition, okay. So, what happens is that we can say that suppose the modulus of elasticity, okay, with respect to temperature theta varies in this way, that at low temperature it is very high and at a high temperature it is low, and this is the Tg, okay. Now, with respect to the frequency omega, the value of E, if I want to see, then it has just the reverse in nature. That means at a high frequency it is very high and at a low frequency it is low. In other words, there is a sort of a correspondence between Tg and frequency, which is called omega critical, okay. So, you can generate a situation like this by changing the frequency or the dynamic condition of the system, okay. So, both way you can get these maximum loss factor achieved in the system. So, this is what I am trying to plot here for you. See the shear modulus plot with respect to frequency, you can see low here, high here, and you can see the omega critical, okay, and you can also see the theta critical, okay, and that is about the modulus part, the real modulus, shear modulus, and then for the loss factor also you can see the peak here. For omega critical you can see the peak here for the critical temperature. So, for both the cases you can actually validate that yes, the loss factor at a particular temperature, at a particular frequency plays a very important role. So, when I choose a material for a polymer, particularly keeping vibration in mind, then I have to be careful about the frequency of application and the temperature range of application. Only when these two are considered together, we should be able to consider the perfect polymer for our application. So, we have completed most of the important properties, okay, that we need in terms of a product design point of view, and some other properties that I have not considered and I will consider in future lectures is in terms of the wear and tear, the tribological properties and the corrosion. They also play important role from a materials point of view of application. Okay. So, these mechanical properties we will consider, and this is important for all extreme conditions. Other than that, for all normal conditions, we have considered all the possible material properties that are generally considered in product design. So, this is where we will put an end of this discussion. Thank you.